Hi everyone, welcome back to Made Everything Official. Inside the Kurt Hydraulics facility, every step of production is driven by precision and engineering excellence. The journey begins as raw metal pieces are placed into advanced CNC machines. Each cut, each rotation, transforms the rough surface into a component measured down to microns. In the forging section, glowing steel is pressed under immense force, shaping durable parts that can endure the toughest conditions. Sparks fly as technology and raw power combine, creating forms that are both strong and exact. Finally, in the assembly area, each part is carefully inspected and fitted together. The process ensures that every hydraulic component leaving this facility meets the highest standards of quality and reliability. The production begins with metal pucks being loaded into the roto-finish system, where they are coated with zinc stearate lubricant. This preparation is essential, ensuring smooth forming as the material enters the high-pressure machines. Once coated, the pucks are guided by a conveyor into the first impact press. In an instant, raw metal is struck with tremendous force, shaping it into the early form of a can. This initial stage lays the foundation for everything that follows. The process continues as an impact machine refines the rough shape. Edges are still uneven, but the body of the can begins to emerge with greater clarity. Each strike adds definition, moving the part closer to its final structure. Next, the cans are flipped and staged for proper orientation. Alignment is crucial here, as the transition leads directly into the end-forming section. Machines and conveyors work in harmony to position every piece with exact precision. The cans then enter a robotic end-forming machine. Automated arms lift, load, and unload parts continuously, handling each one with speed and accuracy. The robots ensure consistency, eliminating delays that human labor could not match. After this, conveyors move the freshly formed cans towards sorting and prepare them for clean room finishing. In this controlled environment, they undergo critical final processes without contamination. Inside the clean room, each can is thoroughly cleaned and carefully dried. The bright metal surfaces emerge smooth and ready for final approval. To conclude, every unit is subjected to rigorous inspection. Only those that pass are packed and prepared for shipment, completing the journey from simple pucks of metal to precisely engineered containers. The Haas VF 2SS is built for high-speed precision, and this demonstration shows exactly why it is trusted across industries. Its spindle reaches 12,000 revolutions per minute, cutting smoothly through aluminum with both speed and accuracy. The workpiece is locked firmly in place as the cutting tool carves out edges, slots, and contours in rapid sequence. Each pass removes material cleanly, while coolant flows to protect the tool and maintain tight tolerances. Chips are cleared away, keeping the workspace efficient and controlled. What stands out is the seamless flow of operations. Tool changes take only seconds, and high-speed rapids move the spindle swiftly from one feature to the next. The machine maintains constant momentum, minimizing downtime and maximizing output. By the end of the cycle, a solid block of aluminum has been transformed into a precisely detailed part. In just over a minute, the VF2SS demonstrates the perfect balance of speed, consistency, and modern CNC engineering. The Haas ST20Y turns precision into performance. In this demo, a bar stock is gripped securely, and the lathe begins its work, rotating at high speed as the Y-axis tool carriage moves into action. The synchronized motion allows for complex cutting operations, facing, grooving, turning, all in one continuous pass. As the tool engages, material is carefully removed, shaping the piece with accuracy and consistency. Coolant flows steadily to protect both tool and workpiece, while chips are cleared swiftly to maintain smooth operation. The Y-axis adds flexibility, enabling off-center drilling and milling without repositioning the workpiece. Transitions between operations are seamless. Tools change quickly, the carriage recovers, and the machine moves fluidly from one feature to the next. Every axis and every motion is choreographed for speed and precision. When the cycle finishes, what was once raw stock has become a finely machined component, with every surface, groove, and contour crafted to tight tolerances. In less than 2 minutes, the ST20Y demonstrates how advanced CNC lathes combine capability and control in modern manufacturing. The SwissTurn Zeit 8-axis Swiss-type auto lathe represents one of the most advanced forms of precision machining. From the very beginning, the bar stock is clamped securely, and the OD turning tool engages to cut along the outer diameter. This initial step defines the outside profile, giving the raw material its first transformation into the shape of a component. Each pass is measured and controlled, ensuring consistency across the entire surface. Once the exterior is established, the NC centering drill moves in. By creating a perfectly aligned pilot hole, it guides the following tools and guarantees accuracy for the rest of the machining process. The 5.1 mm drill extends this opening, pushing deeper into the material and preparing it for larger diameter operations. An 18.5 mm drill then follows, boring wide and smooth passages with remarkable stability, while the workpiece continues to rotate at high speed. Milling operations add another layer of complexity. The 10 mm, 8 mm, and 5 mm milling tools each perform specific cuts, carving slots, refining flat surfaces, and creating fine details. Thanks to the 8-axis design, these tools can approach the workpiece from multiple angles, eliminating the need for manual repositioning and dramatically improving efficiency. Each movement is carefully choreographed, with axes shifting in harmony to produce intricate geometries. As the external and milled features take shape, the ID turning tool begins working inside the component. Internal diameters are cut to exact dimensions, producing smooth surfaces and uniform depths that are critical for the part's final function. Following this, the threading tool engages with precision, cutting spiraled grooves that allow the finished piece to be assembled with other components. These threads must be exact, and the lathe delivers them flawlessly. Throughout the entire process, a steady flow of coolant protects both tooling and material. Heat is controlled, chips are evacuated cleanly, and the cutting environment remains stable. Every second is optimized to maintain productivity while extending the life of the tools. By the end of the cycle, the machine has taken a simple bar of raw stock and transformed it into a fully realized part. Every contour, every drilled hole, every thread is the result of perfectly coordinated automation. This 8-axis Swiss-type lathe demonstrates how advanced engineering and precision mechanics can deliver complex parts quickly, reliably, and with unmatched accuracy, the very essence of modern manufacturing. Welcome to Kurt's Industrial Products Division in Minneapolis, a hub of innovation and engineering excellence. As we step into this facility, you witness a world where metal, machines, and precision converge to bring ideas to life. The facility is equipped with cutting-edge machining centers, robotic systems, and inspection stations. Every section is laid out to optimize workflow. Raw materials enter one end, and finished industrial components exit the other. The flow of parts and processes is seamless, a testament to thoughtful design and execution. Within the machining corridors, CNC mills and lathes hum with movement. Parts rotate, tools engage, and complex profiles emerge under tight tolerances. Each spindle works in sync, cutting, shaping, and transforming billets into intricate components. Robotic arms transport parts between stations, minimizing delay and human error. In the forging and forming areas, heated metal is shaped under enormous force. The team molds high-strength alloys into durable structures that can withstand stress and wear. After forging, pieces often move to heat treatment or finishing cells, where surface properties and resilience are refined. Quality control is woven into every step. Vision systems, coordinate measuring machines, and laser scanners check dimensions and surface integrity. Any deviation triggers immediate correction or rejection. Nothing leaves the floor without Kurt's signature quality. Logistics and assembly lines hum quietly nearby. Once machined and inspected, parts are grouped, assembled, packaged, and staged for distribution. Each movement is deliberate, from bin loading to final shipment. This facility reflects Kurt's commitment to industrial strength and precision. Here, advanced technologies, skilled labor, and strategic layout combine to manufacture components that drive industries forward. The production of industrial lighting components begins with die casting. Here, a 380 aluminum is injected into molds under extreme pressure, forming durable castings that provide the foundation for every part. Massive 800-ton machines handle the process, and a 4-cavity mold increases efficiency, allowing multiple pieces to be produced at once. Once the casting is complete, a trim press removes any excess metal, leaving behind a clean outline. Robotic automation enhances this stage, improving both safety and productivity while maintaining a steady flow of parts. In the next phase, machining operations refine the castings. Secondary processes drill precise holes, tap threads, and smooth surfaces, preparing each part for its final shape. With high-volume capacity, this step ensures consistency across large production runs. Finishing comes next. Deburring and sanding are carried out manually, removing sharp edges and ensuring a smooth surface. Skilled hands complement advanced machines, giving the product its refined appearance. Finally, quality control takes place. Each component is inspected after machining, with critical checks performed to confirm dimensions, strength, and finish. Gears are the quiet backbone of countless machines, transferring motion and power with flawless precision. At first glance, they appear simple, but behind every tooth lies careful design and advanced manufacturing. The journey begins with raw material, usually a high-strength steel or aluminum alloy. Large billets or bars are cut into sections and then forged, cast, or blanked into rough discs called gear blanks. These blanks form the foundation for everything that follows, carrying the exact volume of metal needed to cut the intricate shapes ahead. Once the blanks are ready, they move to gear-cutting machines. Here, specialized cutters gradually carve each tooth into place. The process may involve hobbing, shaping, or milling, depending on the gear's size and purpose. Each rotation of the tool removes a fraction of material, defining the tooth profile with micrometer precision. By the end of this stage, the once featureless blank has become a gear, its teeth perfectly spaced and symmetrical. To withstand the demands of heavy loads and constant rotation, gears must be hardened. Heat treatment is applied to alter the structure of the metal. The teeth are transformed into an extremely hard surface capable of resisting wear, while the inner core stays tough and resilient. This balance between hardness and toughness is what gives gears their long service life. Next comes finishing. Grinding, shaving, or lapping machines refine the tooth surfaces, removing tiny imperfections that the eye can barely see but that could cause noise, vibration, or inefficiency in use. At this point, the gears achieve the exact tolerances required for smooth and silent operation. Throughout the process, strict quality control ensures precision. Coordinate measuring systems and gauges verify tooth geometry, alignment, and spacing. Any deviation, no matter how small, is corrected immediately. Only parts that meet the highest standards are approved to move forward. Finally, the gears are cleaned, polished, and coated with protective finishes to prevent rust and wear. They are then ready to be assembled into gearboxes, engines, and countless industrial machines. From a solid blank of steel to a finely cut, hardened, and polished gear, the process showcases the perfect integration of metallurgy, machining, and engineering skill. These small but powerful components keep the world's industries, vehicles, and technologies in motion, a true marvel of modern manufacturing. Wheel manufacturing for railroads combines raw power, precision engineering, and rigorous quality control. The journey begins with massive steel billets or ingots, selected for their metallurgical properties and durability. These raw forms are preheated, making the metal pliable, before being transported to forging presses. Under immense force, the heated steel is pressed and shaped into rough wheel blanks. This forging process aligns the internal grain structure, giving strength and resilience to withstand the constant stresses of rail operation. Once the shape is formed, the blanks are cooled under strict conditions to avoid internal defects. After forging, the wheel blanks travel into machining zones. Large CNC turning centers engage, cutting the wheel profile, tread, and flange with exacting tolerances. The tool cuts away excess metal, shaping the surface into perfectly concentric forms, controlling diameter, width, and curvature. Cooling fluid sprays ensure both tool and workpiece remain stable in temperature and dimension. As each wheel takes form, secondary operations such as drilling bolt holes, balancing, and facing occur. These steps refine the wheel to precise dimensions and surfaces. The core may undergo stress relief treatments, controlled cooling, or tempering to relieve internal stress and stabilize the structure. Next is heat treatment or quenching and tempering. This process hardens the tread surface to resist wear while keeping the interior of the wheel tougher and able to absorb shocks. Temperature control is crucial. Uneven cooling could cause warping or cracking. Finishing operations follow. Grinding and turning refine the tread geometry, ensuring the rolling surface is accurate and smooth. The flange, tread profile, and rim surfaces are polished to exact standards so that wheels run silently and efficiently on rails. Throughout, non-destructive testing is applied. Ultrasonic inspection, magnetic particle testing, or die penetrant checks detect internal cracks or surface defects. Any wheel failing to meet stringent criteria is repaired or rejected. Finally, each wheel receives a final visual inspection, cleaning, coating if required, and marking before shipment. The completed wheels then head off to be fitted onto railroad cars, destined to carry heavy loads over thousands of miles. From raw molten steel to precision-machined railway wheels, the process reflects the fusion of strength, precision, and quality assurance required to power rail transportation.